In this video, we're going to talk a little bit about what happens when magnetic fields change. What I have here is a galvanometer, which is connected to a loop of wire. Actually, this is about 320 loops of wire coiled up together, and it's all copper wire. What this device does is it's going to detect whether there's a current running in this wire. And as you can see right now, there is no current running in the wire. The marker is directly at 0 here. What I also have is a very large sort of heavy-duty magnet. And as I bring the magnet closer to the wire, what you're going to see is that the galvanometer begins to pick up a current running in the wire. Okay? And so it'll jostle back and forth here a little bit. We'll have to sort of calm it down. Okay. So this happens if I bring the magnet near the wire. It also happens if I bring the wire close to the magnet. And you can start to see that, in fact, I might pick up currents in different directions depending on how the magnet and the wire move. That is, their sort of relative position with respect to each other. Okay? So this observation is something that's quite new in the sense that there is no battery in this situation. There's a magnet and a coil of wire. And so we're trying to understand how do these kinds of observations get explained when we have magnetic fields that are changing in this way. So you might think from back when we did currents that this is due to a surface charge density that changes, right? So that's how we explained how currents ran in wires when we had batteries. So this surface charge gradient produced an electric field that was a constant electric field, and it gave rise to a conventional current that pointed in the same direction as the electric field. Well, let's take this loop of wire, which again is not connected to any sort of battery, and let's see if that model can help us explain this. So I'll draw sort of a thick donut-shaped wire here. And so let's start somewhere. Let's say we have some surface charge gradient. So I'll put some plus charges here, fewer plus charges there, no charge here, some minus charges here, more minus charges there. Now as we go through, this looks very similar to the picture that we have here. So we can identify that there's probably some electric field that runs around the wire, like this maybe, and that would drive a current. But the moment we get to this point here, where there's this huge difference, this huge charge gradient, there's going to be an enormous electric field that points in the opposite direction. And that would conflict with a current that runs around this loop in a circuit, right? So the idea would be that at some point, this current flips around and turns the other way, or something like that. And so this is super problematic, this issue of what happens as you think about a charge gradient in this sort of loop where there's no battery, right? In the case where we had a battery, we could stick it right here and we could deal with that situation. So it must be that there's some new mechanism that is giving rise to this. And that new mechanism we're going to call Faraday's law. And Faraday's law is a mathematical statement of what happens when you have a changing magnetic field. Essentially, a changing magnetic field produces an electric field. And we're going to label it for the moment as ENC because it's actually an electric field that's not associated with static charges. It is a non-coulombic electric field. Mathematically, what we're going to unpack is how this integral of this non-coulombic electric field relates to a change in magnetic flux. This is the mathematical statement of Faraday's law, and it describes exactly what's happening in this situation. So in the next few videos, what we're going to do is we're going to unpack this statement in all of its parts to understand how it actually works. But it goes back to an observation, which is that we can move around magnetic fields, in a sense. We can change magnetic fields around wires, and they drive currents. And those currents are not a result of static charge distributions like we had before.